Filtering in the frequency and time domain is probably the most common pre-processing step in data analysis, I guess, in general, but especially for EEG and MEG data. So the idea is that, well, we start with a signal like that. So these are EEG data as they come from the system after the recording. Some of these channels are noisier than others. I mean, this is probably mostly line noise in this case. So 50 hertz in our case. And what we want is a nicer signal like that. It should look a bit smoother so that we can be confident it's not an artifact, but actually signal of interest. There are still eye blinks in here, possibly other artifacts that we would have to deal with separately. So filtering can't deal with everything, but at least it can remove some of the signals that we don't want. The basics or the basis of all of this is that time domain signals can be represented in the frequency domain and vice versa. So there's a correspondence between time and frequency domain, and we can exploit that if we know or think that we can separate signal from noise in the frequency domain. So the idea is that we take a signal like, let's say, the signal from one EEG channel, we decompose it into sine and cosine waves with different frequencies. And that would basically give us the frequency spectrum, so the amplitude, the weighting that we have to give to all of these different basis functions would be a value in the frequency spectrum at a particular frequency. And here every frequency is represented twice, because in the frequency domain we also have to deal with the phase of the signal. So every frequency can be shifted a little bit backwards or forwards in time. And that would be represented as a phase in the frequency domain. So every frequency is represented twice in the spectrum in theory. So this is also represented here. What we are trying to achieve is that we decompose a time domain signal into its multiple frequency components. So let's just imagine that this signal could be approximated by a very slow sine wave already. A lot of variance could be explained by the slow wave. And then in order to explain even more, you have to add other frequencies as well at certain phases. And the amplitude of these different contributions from different sine or cosines is represented as peaks with different height in the frequency domain. And it looks like we are just making things more complicated. So we are turning one signal into many other signals. But the idea, of course, is that we can then say, okay, some of these signals are what we want, others are signals that we don't want, let's say high versus low frequency, so we can remove what we don't like, and we can reconstruct a cleaner signal in the time domain that we can then analyze further. That is basically explained here. So I had one session before where I talked a little bit about decomposition of signals in general. So the idea is always to decompose your signal into components that, well, are meaningful to you and that allow you to possibly decide, which components are good, which ones are bad. In this case, it depends on the frequency. Then you remove the part of the frequency spectrum that represents artifacts. That could be high frequencies or very low frequencies. And then you recompose your time domain signal from the remaining good frequency spectrum, and that hopefully produces a cleaner signal. And one simple example would be removing line noise that comes from electrical equipment around the MEG chamber, or often also interferes with EEG measurements at 50 hertz here in the UK, 60 hertz in the US. And this can be removed with a notch filter. So you basically filter out that particular very narrow frequency band. Could also be muscle artifacts that are usually present at high frequencies, but one has to be careful because they are also, they can also contaminate the signal at lower frequencies. But this is something you could potentially address with an appropriate low-pass filter, at least to attenuate these muscle artifacts. Unless, of course, you're interested in high frequencies, then you may have to think again. And unfortunately, signal and artifacts often overlap in the frequency domain. Frequency filtering, also temporal filtering, cannot remove all of the unwanted signals. It can only help a little bit. So just be careful with what kind of artifacts you are dealing with, because certain types of movements or heart activity or eye blinks cannot be removed in this way, or they could in principle, but then you would also remove a lot of brain activity. So the golden rule, as always, is avoid artifacts if you can, control for them if you can. I mean, make sure that you have EOG electrodes there. If you're using max filter, for example, you have movement parameters. You can get movement parameters out of it. And sometimes, or often, you also have to use spatial artifact correction methods, for example, independent component analysis or max filter for MEG, to remove some of the some other artifacts that might actually be in the frequency range of interest for you. Okay, but now back to frequency filtering. So you want to, well, by definition, you actually try to change the time course of your data. And therefore, you have to be careful with your filtering settings. So at a very general level, I would say filter as much as necessary, but as little as possible. In order to do that, you have several types of filters available. I think they cover most of, if not all of, the tasks that we want to perform with our data. I mean, there's the high pass filter, and as the name suggests, it lets the higher frequencies pass and it suppresses the lower frequencies. For example, it does something like detrending. So if you have very slow movements, slow drifts in your data, you can get rid of those with a high pass filter. You have a low pass filter that lets the lower frequencies pass, and it removes or suppresses, I shouldn't say remove, I mean, it suppresses higher frequencies. And if you combine these two, you have a band pass filter. So you can apply one after the other. You can apply them together often in your software. So it lets frequencies pass that are within a certain frequency band, and it suppresses frequencies above and below that band. Again, you will never remove these frequencies completely. You can only suppress them to a certain degree. I already mentioned the notch filter. If you have a signal that has a very sharp frequency range, like the line noise, 50 or 60 hertz, a notch filter is basically a special case of a bandpass filter that is designed to remove some very narrow frequency signals. And there is, of course, a lot of information about the details of filtering available in various papers. I think for most applications, you can probably follow guidelines within your software package or from the literature. But of course, if you do something slightly differently from what people have done before you, then it's good to know at least what you're doing with or to your data. It's also important to realize that time domain and frequency domain are two aspects or two sides of the same coin. So as soon as you do something in the frequency domain, you can already say what you're doing to your data in the time domain and vice versa. So in the frequency domain, you might talk about high pass filtering or low pass filtering. And in the time domain, you might talk about smoothing, but these two types of operation actually have a corresponding relationship to each other. This is illustrated here. So a low pass filter can be characterized by its filter characteristics. So imagine this is the frequency scale here, frequency from, there's no particular scale, but let's say up to 100 hertz or something like that. And a low pass filter would let the low frequencies pass. So with a value of 1, it would not do anything to a signal at that frequency. With a value at 0, it would remove it completely. Usually you get filters that filter characteristics that are a bit smooth like that. So you suppress higher frequencies. And this would correspond to a smoothing in the time domain. So what you're doing to your signal in the time domain is basically you run a Gaussian kernel across your data. So at every sample, you replace a sample by a local average given by this Gaussian in your time domain. Different filters would have different kernels in the time domain. So this is not always the case. It depends on what filter you are using. But at least as an illustration, I think that's approximately correct for most of the methods that we are using. A high pass filter lets the high frequencies pass and suppresses the low frequencies. And in the time domain, it looks a little bit more complicated. So here you are taking a difference across time. So if you replace every sample with a local average that includes positive values around the sample and negative values ahead of this time point and behind this time point. And that way you remove everything that's homogeneous over time, that's relatively slow. And you let things pass that are relatively fast, that are not subtracted out. And if you combine the two, you basically multiply them, these kernels with each other, or you convolute them. And so the bandpass filter in the frequency domain, quite straightforward. So you let frequencies within a frequency band pass, and you suppress everything above and below. But in the time domain, you have something that's a bit more complicated. It's a combination of these two friends here. So you compute more complicated local average for every time sample. And in order to jump ahead a little bit already to our time frequency session later, so what does this remind us of? This kind of bandpass filter in the time domain, well, it looks a bit like a wavelet. And that's exactly what a wavelet is. A wavelet is a bandpass filter with some very specific characteristics. So more about that later. But here, the important thing is for everything you do in the frequency domain, you have a corresponding function or operation in the time domain. If you want to look at these things for your specific filter, most software packages should have some functionality to visualize the filter settings. For example, in the time domain, what you're doing to your signal in the time domain should be represented by something called an impulse response or impulse function. So this is basically the time domain here. And in this case, I'm visualizing a filter between 0.1 and 30 hertz. And here, this impulse response is shown for quite a long period of time, so you don't really see much. But if you zoom in, then this is basically the kind of wavelet type response that I mentioned just before. So this is what you're sliding over your data when you're filtering your data. So this is what you're doing in the time domain. It also shows that this filter sort of affects every time point. So every time point will be influenced by time points just before and after in the time domain. This is the filter characteristic in the frequency domain. I mean, and this is in decibels. I'll briefly explain that later. But in this case, 0 means that the signal remains unaffected up to a certain frequency, and then you suppress frequencies above that, and you can see there's not just a smooth function, so you have these ripples here. So you are not really suppressing these signals above 30 hertz completely. There's a certain transition period, and then you have these ripples. You may not care about this in many cases, but you should know that this exists. And also you have a representation of what it does to the phase at different frequencies. And most of our filters should actually not do anything to the phase. So that should also all be 0 here. So the 0 phase filters. And there are various other parameters there's lots of books have been written about different types of filters. I would say most of the time, you can follow the guidelines that you probably get with your software packages. But of course, as soon as you do something maybe more complicated and non-standard, then the more you need to understand these parameters. What does it potentially do to your data? So there are some interesting papers that I recommend. Not surprisingly, it changes the shape of your signal in the time domain. That's basically the whole idea of the filter, but it also means that you can do too much or not enough. So in this example here, there's a simulated signal. There's, I think it's this purple curve here at the top. And then different filters have been applied. It's supposed to mimic and evoke a simple evoked response. So if you filter here with the blue, represented the blue line, 0.1 hertz, it more or less stays the same. So in this case, you might suppress some of noise. Well, there's no noise here, but you leave the signal more or less unchanged. And the more you filter up to 1 hertz, the more you actually suppress the signal, because there is a strong 1 hertz component in the signal. So you're suppressing that as well. And because you have these smoothing kernels in the time domain, you also change the signal actually before the peak, or before what actually seems to be the real signal here. So you actually smooth your signal, or you smear it out over time. So you might suddenly have effects earlier than you would actually expect from the original signal. So this is just something you need to take into account. So you are obviously, by filtering your data, both with high and low pass filters, you are changing the temporal characteristics of your data. And that might be desirable or not. So here's another example, low pass filtering. You could also see that as smoothing in the time domain. you have an ERP, you have some noise here, so the raw data are the greenish turquoise curve. And with different types of filters, you can remove the noise, but leave the signal relatively unchanged. But if you then filter more radically here, then you see that of course, you remove the noise as well, but you also diminish the actual signal of interest. And that is more the case for this earlier response, which is high frequency. So if you remove higher frequencies, this will be affected more. While this later response, which is about more low frequency, I mean, for this component, there's probably this filter, this low pass filter of 7.5 hertz is probably still appropriate. So even different filter settings might actually be appropriate, even within the same data for different questions, depending on whether you look at early or late components or simply the frequency characteristics of your effects of interest. And the same is shown here with an MMN response, a deviant response, where you can see that the early faster responses are suppressed. If your high pass filter is your low pass filter is a bit too radical, while a later, smoother component might actually be appropriately filtered here. Another thing you need to be aware of when you filter your data, it can produce artifacts at signal discontinuities, either big jumps in your signal, or if you're filtering epoch data, then for example at the beginning and at the end of your data segments. This is illustrated here with just some arbitrary raw signal. And obviously these signals, the theory usually assumes that you have signals that go from minus infinity to plus infinity, but that's usually not the case. So it starts somewhere, it ends somewhere. So it's a bit like everything is zero before, and then suddenly something happens, and then it's zero again until infinity. So that would be sort of a theoretical model of these data. And if you then high pass filter this signal and you show it in the time domain, then you see these strange ripples at the beginning and at the end. And that's because there are simply no data points, no meaningful data points before. So in the time domain, you're moving your kernel around these data, and it starts with zero, and all of a sudden there are some data. So the beginning and the end is usually much more variable than the data where the kernel has actually more data to operate on. So these edges are usually not interpretable. How long, the length of the period that you should avoid depends a bit on your filter settings and on your signal, but usually the recommendation then is that you should always filter the longest possible data segment. So ideally the raw data as they come in, to make sure you don't have any problems like that. So if anything, so try to avoid filtering epoch data already. Usually we know in advance the frequency ranges we are interested in. So filter the raw data rather than epoch data. And if you have to filter epochs, then consider filtering, make them as long as you can. So even if you're only interested maybe half a second, maybe cut epochs of 1 second, add a little bit of epoch at the beginning and at the end, and then you can later crop these epochs after filtering. So try to avoid these edge artifacts. And even after you've done all this, just be careful if you see something that looks suspiciously like that, what I've got on my screen here. And if you see something like that, maybe go back to the beginning and see if you can get to the bottom of it. Another thing to consider is the aliasing effect. So this happens if you don't filter your data appropriately before you downsample them. Hopefully, most software packages will have pipelines that take that into account. There's something called the Nyquist theorem. That means that if you downsample your data, then you should have filtered your data with a cutoff, low pass cutoff, with at least half of the sampling frequency. So in other words, there shouldn't be any frequencies in the data above half of the sampling frequency. The reason for that is that if you have, let's say, a relatively high frequency signal, and then you take every 10th point of that signal, it may actually look like you have a low frequency in your signal, which is actually not there in the original signal. So imagine by downsampling, you always happen to be just a little bit, a little bit ahead of the phase, or a little bit behind of one cycle of the original frequency, then you will get this spurious low frequency in your downsampled data. If you had filtered the data appropriately, So then you would probably have seen nothing at all in the signal because you only have one frequency in your original signal. And this is something we often see, at least in older movies, for example. So when you take pictures 25 times per second with a camera, and you film a car and the wheels are spinning faster than that, and let's say with every snapshot, every time you take a picture 25th of a second, the wheel has moved around one time plus a little bit, then in the movie it might look like the wheel just moves very slowly, which can look quite funny. So as children we enjoyed that quite a lot. But this can actually look quite impressive if you look at something like that here. So there's a YouTube video where somebody shot this movie of an army helicopter, and it seems to hover around. So it's not a super weapon. So it's not some great invention, anti-gravity technology. It just means that the camera shoots this movie at exactly the right frequency to make sure every time it takes a snapshot, the rotor blades have just moved around by one cycle. Hence this interesting effect. Okay, enough of that. Okay, this is the movie. And finally, I mentioned decibels earlier. So quite often you will have to deal with signals that are expressed in decibels. Well, I mean, if you're interested, look it up on Wikipedia, for example. It basically turns your signals into a logarithmic scale, and it expresses signals as a relative strength of your signal with respect to some can be arbitrary reference signal. And it is often used to describe the attenuation of filters, but also the frequency content of data. So this is the formula. So the new signal, if you have a signal P or signal strength P, actually the power P, then you can express this as a ratio of this power to some reference value. You take the logarithm to the base of 10 times 10. And because the power is the square of the original amplitude, you can pull the number 2 out. So it's 20 times the logarithm of the ratio of the original amplitudes. There are certain characteristics of the logarithm that are convenient in signal analysis. So engineers like that. You basically have a different scale for your data. So you have these different orders of magnitude represented on a slightly narrower scale. So this is the decibel value here, power ratios, and then the amplitude ratio. I mean, this is just the square of the amplitude. And the reason why we do that, or one of the reasons at least, is that it's a better way to compare different effects in different frequency ranges. So usually frequency spectra have this 1/f characteristic. So they're basically a very large at lower frequency and then smaller at high frequencies. And that makes it sometimes a bit difficult to compare across frequencies. If you turn this into logarithms and decibels, you usually have frequency spectra that are a bit more flat. So this would be the amplitude of the filter characteristic expressed in decibels. And this would be the actual frequency spectrum of EEG and gradiometers, magnetometers expressed in decibels, so dB here in the scales. And it just shows that you have an almost flat spectrum apart from lower frequencies. And then it also shows you that the filter indeed worked. So not much above 30 hertz or 40 hertz, don't remember exactly, or 35 hertz, what the filter was. So you just have to be aware that sometimes you will come across this decibel scale in the literature. And that's it for now. Thank you.